All right, now we can get going. All right, we're looking at nuclear chemistry, and in this one we're trying to understand the particles. So there's different types of decay: alpha, beta, gamma, positron emission, and then not a decay but an electron capture of bringing it in. So what you need to understand is the mass number and atomic number of each. You can see how they kind of change. And remember, the bottom number is the idea of a of the atomic number. So something like an electron would be -1, while a positron, which is essentially a positive electron, would actually have a +1, but you see no mass number. Because a mass number is the protons plus the neutrons, like in an alpha particle would be 4, 2 protons, 2 neutrons. So be comfortable with the idea of the symbols, what they are with the nuclide symbols, and kind of how they would be used. I mean, changing how they would change is something you can interpret based upon there, but we're going to be doing some of these equations as your completion for that. So think of that in mind. Another part that you've got is the particle's power. So an alpha particle will be blocked by a piece of paper. Beta particle goes a little bit through your skin. X-rays, which again are not part of our things here, but gamma rays are much further. We need cement to get stopped. And neutrons are not mentioned as a part of decay, but is a part of some penetrating power. Now, another part that can be damaging for people is the ionizing power. The ionizing power is due to its charge. So an alpha particle has a charge of +2, therefore is the most ionization penetrating power. However, beta particles or positrons have a -1 or +1, so therefore are less. And things like gamma rays and neutrons even, they have no charge at all, so their ionization energy is nothing. So they are the weakest in that sense. All right, so now we're going to look at relative stability. Now there's a lot of distinctive rules that you'd have to follow and figure out in order to determine if something is stable or not. We're not going to go to that granularity with it, but you do need to understand some basic ideas. So the first thing is atoms with above an 83 as their atomic number are radioactive and will decay. So that's a big giveaway. You don't need to know the types. I just include it mostly that they're giving off electrons or breaking down and giving off big alpha particles. One of the things you should realize, though, is that when the number of neutrons and the number of atomic number is even, that's a very good sign that it's going to be less likely to be radioactive. When you get either of them odd, kind of a little bit more of a giveaway. And then when they're both odd, oh my gosh, definite giveaway. So odd generally means radioactive. Even generally means not radioactive. Now, there's this relationship between atomic number and neutrons, and essentially 1 to 1 is going to be best. If it's too high, then the nuclides that lie above that valley of stability have too many neutrons. They tend to convert neutrons into protons. This process of undergoing beta decay moves down the nuclide until it gets into that valley of being kind of a 1 to 1 ratio. If it was too low, the nuclides that lie below the valley of stability, you have too many protons and tend to convert protons to neutrons via proton emission. Again, how would you be able to change the protons if that relationship is too high into neutrons, or changing neutrons into protons? And that has these different ideas. You don't need to memorize the valley or anything like that, but the idea is that closer to 1 to 1 is better. All right, so let's look into what we've got coming up next with balancing. So essentially what you're trying to do is balance the atomic number at the bottom and the mass number up top. So if you have on the left 241, I'm going to have 241 on the right, which means this has got to be a 4. If I have 95 and 93, this has to be a 2. And the thing that has an atomic number of 2 is helium. Same way over here. So if I have 233 and 0, that means my mass number has to be 233. Down here, 92 plus a -1 would be 91. And what is the 91st element? PA. All right, so it's just a simple accounting here. Again, if we have 4, that means this must be 233. This must be 91 because of the fact it gave off a helium, and 91 again. So same particle, but you can see this one is either breaking down to make uranium or neptunium breaking down to make this Pa. I don't even know what that one is. Oh well. Likewise, it could happen things with smaller. So if we have a 0, then that means this must be 75. And if this is 35, this must be 34, because it's 34 plus 1. Be careful with looking at that. A lot of students can easily get that wrong. This is selenium, just because they happen to look at it wrong. Not pictured here is electron capture. Can be aware of it. Remember, that could be some of our particles. And be comfortable in determining these particles as well, that they can work. And keep in mind, if you got gamma, that would be 0 over 0, not just nothing. There's always going to be something as a particle. When they give you these lines, they're indicating something's there, not just nothing. All right. So be comfortable finding the bigs and the smalls. You'll get a good amount of practice on Pearson. Let me know if you have any kind of questions. See you soon.